Another thing we potentially do is do the luminescence of iodine with the argon ion laser, so that's another possibility that we could explore.
So you are rolling.
Okay, so we want to keep on rolling. They're doing some publicity filming, and there may be some people that come and interrupt us at 2:30.
Okay.
I don't know if they're going to be on time or an hour late. It may not even happen. But if people start barging in the door, at least you'll know why. Okay. We, in our last class meeting, we were talking about the electric dipole transition operator. And if you'll recall, we are we plugged in and set up yet?
You're rolling.
Okay. If you'll recall, we said there are different ways for electromagnetic radiation to interact with atoms and molecules. And by far the most common is the electric dipole mechanism. And we were looking at some of the background quantum mechanics for particle at a ring. And we had identified the electric dipole operator as the way the radiation interacts with the atom. And we were kind of doing some of that right here on the board that is in front of us. So let me open the class here this morning, or this afternoon, it is actually, by asking if either of you have any questions or issues kind of stemming from our last lecture and from the material you're starting to work on. So the floor is open. I want this to be interactive and make sure that that I'm giving you a good response to everything that you're doing. If not, we can just kind of go on and continue to look at things.
Yeah.
Should we just go on?
I guess a lot of these problems have to do with transition moment integrals and.
So have you been trying, like in exam 3, have you been trying some stuff?
Well, I look at it, but then like I don't know what to do about transition moment.
Oh, okay. So maybe we should, because we're ready essentially for a transition moment integral.
Let's do it.
And let's see if we can set one up. I think I'm just going to start by erasing the whole board. Now what you're doing in molecular spectroscopy is we're using group symmetry to figure out whether selection rules are 0 or non-zero. Here we're just going to beat through with the calculus.
Okay.
Okay, let's get this board erased. Okay, so let's look at a specific thing. We had done, we've gone a long way on our way to finding the expression for the electric dipole operator. By the way, this is the 31st. And let me get a marker that marks for that. 33116. So we had got, if I recall correctly, we got an expression for problem number 3 on exam 3 at the end of the hour. And I'd like you to just tell me what that is. So the electric dipole operator is the oscillating electric field vector of the light dotted with the dipole moment of the system. So what was the end result of that analysis?
So.
Okay. So we've taken the dot product. What was the final result?
You got big E times little e.
Okay.
So big E, little e r sine of k WT times sine phi.
Okay,
Yeah, that's
so this is the okay. So the sine gives you the oscillation. The sine phi is where we happen to be in the circle. So if we look down on this, you know, I and j unit vectors working down on this. Our particle is going around in a circle of radius r. So here we are, and here is our angle phi. So that's our picture, and the sine of this is r sine phi, and this projects us along the y-axis. And if you'll recall, we are dealing with y-polarized light, so that sine phi gets us in the y or the j direction. Does that make sense? These are the correct expressions for a dipole moment times an electric field. So let's now see what the whole transition moment integral is, okay? So in the Dirac notation, this is our transition moment integral, minus E dot mu, quantum state 1 of particle in a ring to quantum state 2 on particle in a ring. And by the way, what is the only coordinate for particle in a ring that changes? There's only one coordinate that changes during the problem. Is the radial part fixed? Yes, the ring radius does not change. So the only thing that changes is the angle phi, okay? So we have quantum state 2, so this is the integral from phi equals 0 to 2 pi of our quantum mechanical operator for state 2. So this is 1 over the square root of 2 pi e to the I, and now let's put a 2 here, e to the I times 2 phi, because it's quantum number 2. That's starred. Then we put big E, little e, r, sine kz minus omega t, sine, and this is sine of phi, and then 1 over the square root of 2 pi, e to the I phi d phi. Okay. Now, what I clearly want you to see this is quantum state 1, and this is quantum state 2. And this is minus E dot mu for Y polarized light. So do you see it? Do you see kind of, here's Dirac over here, And here's Schrodinger over here. And now I want to pull out of the integral everything that doesn't have the variable phi in it. So what do? So we've got square roots of 2 pi, so those can come out of the integral, right? That's 1 over 2 pi. And then E, big E, little e, r, sine kz minus omega t can come out, because there's no phi involved. And now we have the integral from phi equals 0 to 2 pi. E, and what's the complex conjugate? If it's e to the I2 phi star, what does that mean?
Turn into e to the negative I.
Right, so this is e to the minus I2 phi. And then there's a sine phi, e to the I2 phi, or I1 phi, d phi. Now, can you suggest how to proceed?
You can combine the e's.
You can combine the e's, okay. So this is phi equals 0 to 2 pi, e to the minus I phi, sine phi, d phi. Okay, now tell me how to progress. Do you know what the Euler relationships are for complex exponentials? Okay, those are the Euler relationships. Now, you can either convert everything to complex exponentials, or you can convert everything to trig functions. This is the class's choice. So I'm taking, it'll work either way. So do you want to convert, do you want to go trigonometric, or do you want to go exponential?
Let's go exponential.
Okay, fine. Okay, this is a sine phi, right? So if I do e to the I phi minus e to the minus I phi, the two cosines cancel out, and I'll get 2I sine phi. And therefore, 1 over 2I e to the I phi minus e to the minus I phi equals sine phi. Substitute in for the sine. And what do I get? Phi equals 0 to 2 pi. E to the minus I phi times, and we'll bring the 1 over 2I outside, e to the minus I phi times e to the I phi minus e to the minus I phi d phi. Okay, carry into the integral everything, 1 over 2I phi equals 0 to 2 pi. And now, what's e to the minus I phi times e to the plus I phi?
2e.
E to the minus I phi is 1 over e to the I phi. So what's e to the I phi divided by e to the I phi? 1. So the first expression is 1, and the second one is minus e to the minus 2I phi. D phi. Okay. And by the way, all this stuff I got carried away in my integral. So everything that I'm coloring in pink here still exists right here in this little circled region. Does that make sense?
Mm-hmm.
All the pre-integral factors that we factored out are still there. Now, let's settle this integral. This is coming around here. This is the kind of blackboard we should show freshmen and say, are you really man enough to do this curriculum? Okay, so I can break the integral up into 2. Okay. So I want you to do the integral on the left. You do it. Give me the answer right now.
That would just be pi.
It's 2 pi. So this is, yeah, the integral is,
Oh, okay, so, yeah.
okay, whatever, all that junk. So the integral on the left is phi between 2 pi and 0. And the integral on the right is 1 over 2 pi e to the minus 2 pi phi, evaluated between 2 pi and 0.
Is that 1 over negative 2i?
Yeah,
Okay.
because when I take the derivative of this, it's this times whatever's in there, and that minus 1 over 2i comes down to the denominator, okay? So, what do we get? And this whole thing is in brackets. So I'm, again, running out of board space, but let's press on here. So we've got this over 2i. Okay. It's that 2i. And then phi between 2i and 0 is just 2 pi in the first term, minus, and now we have minus 1 over 2i, and then we have e to the minus 2I times 2 pi minus e to the minus 0. Okay, what's something to any, if you raise anything to the 0 power, what is it? So the second integral, this is 1. And then what's e to the minus 4 pi?
What happened about the I?
Oh, 4I pi.
Negative I. So
If you go around the complex circle, or you can write this cosine 4 pi plus I sine 4 pi. The sine of any multiple of pi is 0. The cosine of 2 times around the circle is 1. So this number is is 1 also. And what's 1 minus 1? 0. That whole piece drops out. Okay, so what we're left with is a non-zero transition moment integral. And now let's see if we can write down all the pieces. 1 over 2 pi, big E, little e, r sine kz minus omega t. There's all that. And then all this is divided by a 2. Should this be a 2I or a 2 pi? It is a 2I, isn't it? Okay. Over a 2I, and then in this integral we have a 2 pi, right? Okay, so we have this 2 pi and that 2 pi cancel out, and we have this transition moment integral left. And the important thing for you to see is that it's non-zero. And what that says is the radiation can deform the n equals 1 orbit into the n equals 2 orbit of this molecule. Or this prototype of an electron orbiting in this orbit. Now, what have we learned from doing this transition moment integral? We've learned that even for a simple system, they can be complicated, can't they? But that if we apply our standard knowledge of calculus, we can come right through and get it quite nicely. Okay? Now, since I've done this, what should you do?
Write it down.
Now, oh, here are the camera people. Are you looking for Founders Hall 200?
Yeah, that's it.
This is like the cool room. Well, there are more than one cool.
I was told it was at the end, I didn't know which end.
This is the living end.
I love it. Hi.
What's that?
Okay, and I warned these guys that you might be coming in on us.
You're here, yeah.
So tell me what you want to shoot and we'll see what we can come up with.
That is a good question. So basically, what do you guys do in this room? Tell me.
Oh, I torture students in here.
Oh,
And
okay.
you don't believe me, look at the board.
And yeah, and so, I mean, basically whatever you normally would do, whatever you think is visually stunning.
Okay,
We are-
so we can,
Get a shot of us. Maybe look. Are you taking picture or video?
We're taking video. So it would
Okay.
just be the interaction with you guys. If there's a machine that does something pretty cool, you can let us know what it does and we can talk over how we would like to shoot it and then warn you guys what will we do.
Yeah, I mean, we can make this pretty short as long as, like, what we're looking to do is kind of like build a little story in here.
Yeah.
The way that we do that is with a sequence. So if you're talking about a lesson, you know, obviously we can get you already on the board, we can get you guys paying attention.
Yeah. Do
And
you
then,
want us close together, maybe?
Yeah.
And then you guys get like a back view or something.
perfect, yeah, we'll get
Yeah.
you guys together, and then whether that's like using one of these machines or something like that that is turned on with goggles around it or something like that,
Yeah.
and that's kind of what we're looking for.
Yeah.
okay, we can get some goggles.
Okay, yeah, that's great.
Do you want to do? Considering we're listening to him right now, do you want us up here, maybe listening to the lecture?
Yeah, that'd be
You want
good.
that type of shot?
Yeah, we can get you guys both like right here. And just, obviously this will be something we can show the intimacy of the class too.
Yeah, so why don't you guys pull up here?
And grab your notes and stuff, and we'll kind of peek over your shoulder with you, like writing some notes and things like that.
Let me see what the latest is too.
I mean, it looks classroomy. Yeah.
You saved them, I was just about ready to lay another big mean
Uh-oh.
assignment
Pop
on it.
quiz or something?
Wow, pop quiz.
If I push this chair.
Yeah, you can push that chair. You can take this chair and shove it.
And what class is this?
This is physical chemistry.
Physical chemistry.
Okay.
So what's something that we can do in this room also? So we'll get.
Oh, we can simulate you playing with the instruments.
Okay.
Perfect. So.
And you can go all the way around and come on this side, like you can shoot this angle, and you want to come back here and kind of get the board and me from behind. You can do that. Just whatever you want to do will, within reason, accommodate you.
I'm gonna stand up here for a bit so I can get their eye.
Sure.
And him writing.
42.
Yeah, I'm at 42 right now.
Is that what you want on that? Yeah, right. I was gonna drop it to like 9.
Yeah.
That's a little more natural.
Okay, I'm just gonna keep on lecturing,
Yes.
and,
We'll
and
direct
then
you.
and I'll just pretend you don't exist.
Yes, that's perfect.
And I'll keep beating up on these guys.
I think it's about 3.5.
Okay, so
You can do it. Oh, sorry.
let's kind of go back and look at what we've just done. We have the electric dipole operator, and this is for a wave that's propagating in the z direction. So it's going this way or coming out of the board. So it's coming out of the board or going in, and it's oscillating at the frequency you can calculate.
Yeah.
And the radius is fixed. This is the charge on the electron that's going around here. This is the strength of the electric field. And basically, if you oscillate the field the right way, you can perturb the orbit. You can change the way this electron oscillates. It goes around the orbit. That's what we're doing. This is the transition moment integral we just calculated. So this is our quantum state 1 with quantum number m initial equals 1. And then our final quantum number is m final equals 2 in this example. So we went from the Dirac notation, which is very compact and very beautiful, to the Schrödinger representation where we can show all the details of the calculus. So Now, instead of just 2, we have the whole quantum state 2 with the quantum number, the final quantum number, m final equals 2. The complex conjugate, here's the operator right in the middle, and here's the one with an initial state, m initial equals 1, and we can just put it right there to remind ourselves. And then we're integrating over the full circle, which is from 0 to 2 pi radians. And literally, the whole rest of the problem from there, from this point, is one of simplifying, pulling out of the integral expressions that do not contain the angle phi. So all that stuff came out because it wasn't there. And then using the Euler definitions.
Do me a favor and just pretend like you're taking a note.
Oh, yeah.
Yeah. I really can't even see what you're writing, so you can write, this is stupid if you want.
So we use the Euler equations
And then do that again where you're kind of like looking down toward your note.
that
And
that
then,
relate the
like,
complex
looking back
exponential to the cosines and the
And we'll write that down.
sines.
Just kind of keep like, you know, you're
We
paying
substitute
attention,
this
you're writing
in.
it down.
And from here on is basically just calculus. Just
Yeah.
going through the individual
Sorry, you can
steps.
see me in your glasses.
Now, I've given you,
Pretty much helped us with that problem.
I mean, we've taken this problem
You're welcome.
from one end to the other.
Yeah.
So the same thing, just keep taking your notes down and like looking at them. Just kind of build a little thing here. And then-
Okay.
I'm sorry, what's your name?
EJ.
EJ, you can just keep looking straight. And then your name is, I'm sorry?
Sorry.
Sai?
Yeah.
Sai and EJ.
Psi and EJ. Okay.
Mine
Now, let's see if you can tell me how to write the Dirac. So this is the transition moment integral.
Yeah.
And then Professor, is it possible for you to do like one of those large equations so I can get like the whole thing of you writing it out? Or like, you know, maybe like almost, can you rewrite this, for example?
Oh yeah. Well, I actually have another one I'm going to write
Okay,
this
perfect.
instant. Okay. So I don't even have to fake it.
Where's that gonna be so I can be focused?
I can put it up here. Why don't we put it up here?
Okay.
Okay, so let's go from m initial equals 1, our initial quantum number 1, to a quantum state m final equals 3. So for this case, going from quantum state 1 to quantum state 3, how would I write in the Dirac form the transition moment integral?
It would be,
Go ahead.
yeah, it would be like the same thing, except the first number would be 3 instead of.
Okay, so you start at state 1, you have the operator minus E dot mu, electric field dotted into the dipole moment. Then our final state is quantum state 3.
Feel better energy when we're close.
Okay, so that, was that good enough?
Yeah, that was perfect.
Okay, now, how would
And then
going
EJ,
from-
go ahead and take your note over there too.
How would going from 1 to 3, if we were to set up all the mathematics from quantum state 1 to quantum state 3, what would be different?
Then go ahead and look up towards Professor EJ.
Everywhere you've got.
Everywhere I have
Yeah.
a 2 in the exponential, I would now have a 3.
Yep.
Okay? And
Then go ahead and
we
look down and
wouldn't
take your note.
know until we carry that through whether integrals that were non-zero before are 0 now. But the thing I'm looking for is, do you see the general picture of what we're doing? And can you go from Dirac to Schrödinger? Can you go to something like this? And we could say, you know, I could modify this whole thing. I could say, this is now 3, and everything else is the same. And I could go through the whole deal, couldn't I?
Yep.
And I could repurpose this whole thing, taking things like a 2 and turning out, so this This would go to a 3 right here. And notice that would change everything, wouldn't it? You have e to the minus I2 pi, and it go to a 3 pi, and so you
I got
have
everything I
different
need.
integrals
I'm gonna
right
basically do
here.
the same thing, but in real time.
Awesome.
Okay.
Just doing one more equation.
Well, what
I'm
are,
gonna just do the same exact thing, but I'm gonna shoot it in a different frame right now, so that way it's just
okay, well,
looks different.
actually, I'll do a slightly different one.
That Steadicam is solid.
Thanks, man. Appreciate it.
Okay. So, we could say
Record would be good. See, it doesn't work if I don't hit record.
the integral is going from phi equals 0 to 2 pi of psi m equals 3 star minus e dot mu vector psi m equals 1 d phi. So that's what that is. And what would this be? What, I want you to tell me, what would I write here for psi m equals 1?
Oh, I know this.
Yes, you do know this. I'll give you a hint. It's 1 over the square root of 2 pi, and it's e to something. E to the I something.
E to the I1.
E to the I1 phi.
Yep.
Okay, and what would I write here? I'll give you a hint again. 1 over the square root of 2 pi.
Go ahead and write your note real quick, DJ, and then
E to the what?
it's perfect.
E to the I 3
And
5.
then go ahead and look back up.
I 3 phi, but it's complex conjugated, so I put a star on there.
Same thing for you, Si. Go ahead and take your note.
Now, look at this. How do I take the complex conjugate?
Look up.
So if I, what does that star do to this wave function? Okay, that star does what? It does something to an eye.
Stay back just for 1 second.
Yeah.
Turns it into a negative eye. That's exactly
Get all the
right.
tights you need.
So it's 1 over the square root of 2 pi e to the minus I times the number 3
Good.
times 5. That's exactly right. Okay. Now, what is the wave function? What does that wave function look like?
M equals 0.
Can I have you just go directly, there, and write something on the board there?
Okay. Now,
If that's at
not
all
any
possible.
professor can switch hands.
There you go. These ambidextrous.
Yeah, so you,
Just
okay.
somewhere below,
So you want it right here? Can I erase something?
Yes, you can.
Okay. Okay, now, will this work?
Yep, that's perfect.
Okay, I am left-handed, I'm gonna start with the left hand. So, I wanna know what psi m equals 0 of phi looks like. Ta-da!
0.
No, but a good guess. Okay, let's do the form. It's 1 over the square root of 2 pi. And now what do I write?
Psi
We've been writing it all along.
E
E to the what?
I
I
0.
0
So it'll just be 1.
phi. No, the wave function will be.
No, E to the I 0 would be 1.
Okay, so it's e to the I 0 phi. And what's e to the 0?
1.
1. So this
1 over 2 pi.
This integral is 1 over 2 pi. Now, I'm going to ask you, why is the square root of 1 over 2 pi there? There's a reason why it's there, and nothing else is there.
That's the limit.
It starts with the letter N. This wave function is normalized. Exactly right. So you know more than you think you know. Okay, so a normalized wave function says if we go from phi equals 0 to 2 pi.
Is this really relevant, or are you just kind of doing this?
No, it is relevant.
Are you guys?
I'm not entertaining these idiots. I'm teaching you.
Is there any way that we can pause the class
Yeah.
and do something
Yes,
fun?
they don't want any more of this.
Okay.
They're reeling under the blows. Now, I need to quickly tell them one thing. This is you don't have to film this. This is scientific. Psi star m equals 0, psi m equals 0 d phi. If we put those in, it's the integral phi equals 0 to 2 pi of 1 over the square root of pi times 1 over the square root of 2 pi d phi. And that's the integral of 1 over 2 pi, 0 to 2 pi of d phi. And you see the 2 pi's cancel out,
Yep.
and you get 1. So that square root of 2 pi has to be there, normalized.
Got you.
Okay, we should show goggles
Yes.
and gloves.
Yes. Safety.
Okay, so we don't want photos going out.
Yeah, just something that looks cool. We can get you guys kind of around, like, you know, pointing to it or doing whatever
Now,
it
do
is,
you want
hands-on
do you want
stuff.
any of these instruments? Do you want